So a little, again, definition. You don't have to write that heading because we just put covalent bonding. So to write covalent bonds seems a little redundant. And this is good information. So as per normal, when we look at something new, there's a few slides of information that need to be given. But then we will get into some practical drawing, Lewis diagrams. We'll be using our energy level diagrams to represent sharing of electrons now. So the ideas expressed in this slide come from our Lewis idea of bonding, and we've used that before. We're going to use bonds, single bonds, double bonds, triple bonds to represent shared electrons. In grade 9 and 10, you would have been informed that they were sharing them. Last year I said it's not quite a share, it's really more of a tug of war. And now with our ideas of orbitals, we have, again, a little more of an expanded way to think about what's happening to those electrons in a bond. So we'll be extending this idea. Again, this is still the Lewis idea, right? They need to share enough in order to get a stable octet, 8 electrons in the outer shell, with hydrogen being the exception. And we'll find out that boron and beryllium are also an exception. The shared pair of electrons are found between the nuclei of the two atoms. I'll expand on that in a moment. The number of covalent bonds an atom can form is equal to the number of unpaired electrons in its valence shell. And we've already seen that before. Something like nitrogen has a pair of electrons and then 3 lone electrons. It's going to be able to form 3 bonds. All right, and that's stuff from last year. Now, to bring this in line with our quantum view, the theory that we use to explain what happens to orbitals is called the valence bond theory. So in the valence bond theory, we don't have, 2 atoms sharing a pair of electrons. We have our electrons existing in this area that we call the orbital. And again, keep in mind, we really have no knowledge of where the electron is in that orbital, but we know it's going to be there 95% of the time, as determined by the calculations. So now instead of sharing electrons, we have atoms who get close enough together that their orbitals overlap with each other. If we keep in mind the fact that an orbital is what we call a probability wave function, where it is a wave that describes where we will most likely find an electron. So if an orbital is a wave, you can have 2 of these waves interact with each other. And in physics, and I mentioned this earlier on, and those of you who have taken the physics, you would have learned that when you have waves overlapping, you get something called interference. You can have constructive interference and you can have destructive interference. And when two orbitals overlap, to produce constructive interference, the wave gets bigger. That's just a law of physics. That's nothing to do with quantum mechanics. But if you have then the probability of finding a single electron in its own atom and its own atom, and then you overlap those functions, the wave grows in the middle, in between the atoms. It gets bigger because we have constructive interference. And if the wave is bigger in the middle, there's a greater probability of finding those two electrons now in between the atoms. And that's what we think of as a bond. A bond is when we have two orbitals overlapping to form constructive interference such that the electrons are now more probable to be found in between the nuclei, and we have a bonding situation. How does that actually bond? Well, if you put two negatives in between two positives, there will still be an electrostatic force of attraction on those positives holding them together. So they're still being held together by electrostatics, but quantum mechanics is going to tell us that the electrons are now going to exist in between the nuclei more often, and therefore we have this attraction. When we have this new orbital created, and it's a new orbital created by the two atomic orbitals, we call it a bonding orbital, all right? There's another theory that is just slightly different than this one that's called molecular bonding theory, and we would call that bonding orbital a molecular orbital. And I'm going to use those terms interchangeable, a bonding orbital or a molecular orbital. It's simply an orbital that's in a molecule as opposed to atoms by themselves. What you learned about on the quiz are atomic orbitals, the orbitals in the atoms. What I'm going to be showing you today is the formation of molecular orbitals, orbitals that exist between two atoms in a molecule. All right? Okay. So we've got this idea now of overlapping. Let's start putting some of these orbitals together. And we're going to be doing so by drawing our classic energy level diagrams. We're going to be dealing with Lewis diagrams. We're going to be dealing with eventually three-dimensional Lewis diagrams. And I'll talk about that in a moment. The first atoms we're going to deal with are actually linear atoms. They're made up of two atoms. They're diatomic. So we don't have any three-dimensional situation we need to take into account. But we will soon get to that. Now I'm going to start off this analysis by drawing the energy level diagrams because that's what we've just been working on. Then we'll do a good old-fashioned electron dot diagram, which we won't be doing a lot of, just to kind of get us going in our minds. Then I'll remind you of a Lewis diagram, and then we'll do an orbital view. Once we get going in drawing these molecules, I'm going to rearrange the order of those diagrams. I'm always going to start with a Lewis diagram, because that's something you know how to do. And I'm going to be linking then the Lewis diagrams to things like the energy level diagrams and then our orbital views. What do the orbitals actually look like? So for an energy level diagram for H2, it's pretty straightforward. We're going to be drawing our atoms, H, 1s, it's got one electron in it. Nice simple energy level diagram. And down below it, I'm going to draw a second H, and I'm going to make sure that my orbital is in line. It's a 1s. Just to make life a little easier, I'm going to put its electron upside down, but it doesn't have to be. It'll do a spin flip if it needs to. And now I'm going to represent the overlap of these two orbitals. Remember, in an energy level diagram, those circles don't really mean that they're spheres. They're just places to put the electrons. So in order to represent a bond, I really don't need to have them actually overlap. All I'm going to do is I'm going to put a rectangle around here to represent the fact that those two have got together in some way. So again, keep in mind, this is just a schematic diagram. This isn't what we actually would see. And this particular type of bond that is formed between two 1s orbitals has a name, and this thing is a sigma bond. Sigma, all right? Sigma looks like this. All right, it's a lowercase Greek s, so it's a sigma. All right, let me try to draw it on the board maybe a little bit. Sigma, kind of like that. Capital sigma looks like this. All right, that represents some. Sigma looks like that. And that is called a sigma bond. All right? And the reason it's called a sigma bond has to do with the way in which the orbitals are overlapping. We're going to learn that there are two fundamentally different ways in which orbitals can overlap. And the simplest way is a sigma bond, and it just means that we've got simple end-to-end overlap. All right? So if you were to represent a sigma bond, you could represent it with a handshake. Very simple end-to-end overlap of the orbitals. We'll talk a little more about sigma bonds in a moment. So let's now draw the electron dot diagram so that we can recall how to draw the Lewis diagram. I'm only going to do this once for you. This is the classic H. Very nice. And here we've got the H here, like that. And we'll make it an X. And then we're going to bring them together, and we got our good old H. Very nice. We have our single covalent bond in there. We're going to be drawing lots of Lewis structures. Don't even bother writing the term structure. Just write Lewis. And you can squeeze that in wherever you're putting it. And we know that we can take that pair and we can draw this like that. And we know from last year that this particular thing is a single bond. But we have more information now. We also know that it came from very simple end-to-end overlap. A single bond is always a sigma bond. And we're going to get away from single bond, and we're going to be starting to talk in terms of sigma bonds. All right? I think the reason they use the term sigma is because the first kind of ideas they had with this typically had s orbitals overlapping. So the Greek for S is sigma, so it represents the simplest overlap that you can have between two spherical orbits. But we now know we can have sigma bonds between p orbitals as well. All right, and so we'll see that in a moment. Okay, so orbital view. Orbital view is pretty easy in this case. Now, I'm going to have you do orbital views in your notes. I am not going to make you do pages and pages of orbital views on a test because they're pretty complex. But I think it has purpose in order for us to visualize what's happening in terms of actual orbitals. Very straightforward here. There, and I'm just putting in the nucleus there. That would represent the nucleus. There's our 1s. We're going to add that to another nucleus right there. I'll be honest, when my professor put that on the board, I giggled. Sorry. It's just me. He says, "What's so funny, Mr. Sanders?" Anyway. When you have those overlap, you end up with a situation that looks like this, where you've got a larger probability of finding the electrons in between. All right? And when I represent this, when I start drawing other orbital views, I'm going to draw it like this. Okay, so they're actually overlapping. All right? And in that overlap space, I like to put the little sigma to represent the fact that we've got a sigma bond there. But in, I guess, reality, and that's hard to test, but according to the valence bond theory, when you add these overlapped orbitals together, you get a greater amplitude because their constructive interference is taking place. And so it actually looks more like this. You've got a greater probability of having the electrons in here than out here, and therefore it holds the molecule together. All right? All right. Let's take a look at some other examples. Oh, no, first we're going to define a sigma bond. Direct end-to-end overlap. And I guess just to give you a little look into the future, the other type of overlap we can have for orbitals is sideways overlap. So orbitals coming together in a sideways fashion as opposed to an end-to-end fashion. And this becomes more apparent when we start dealing with p orbitals reacting end-to-end. And this is what the computer gave me as a sigma. You can see there it's like an O with a funny little tail on the top. I don't know how that looks. I don't know if that's supposed to look anything like an S. I don't know. Not necessarily, I guess. So a single covalent bond is always a sigma bond. So if you've got a single bond, you're looking at it, you're thinking sigma bond. It's got to be due to end-to-end overlap of some orbitals in some way. Now, for my next example, I'm going to do F2. You can put example F2. And I am going to have you write down a little description on what the bond is like in an F2. But then I'm going to switch to the Smart Notebook because I've built some little things that I can make it go a little quicker. It'll be neater for you to see. So F2 formed when two 2p orbitals overlap to form that single covalent bond. Now, the first thing we're going to do is Lewis, and now I'm switching the order on how I want you to look at these things. I want to always start with the Lewis diagram, because the Lewis diagram is where you're going to start your analysis of a structure. Over the next 4 and 5 classes, I'm going to be expanding your view of what those atoms and molecules look like. And the starting point is always a Lewis diagram. By the end of this procedure, I'm hoping that you can just look at a Lewis diagram and be able to think about what type of bonding is in there, and in the end, what's the shape of that molecule. You should be able to do this. If this process works the way I hope that works. So I'm going to switch now to the Smart Notebook. All right? And I've got my slide up for H2, but I'll switch that over to the next slide, which is going to be F2. And again, I've got all that information that I want to do. Lewis diagram, energy level diagram, the orbital view. I don't need this 3D Lewis yet because we're talking about linear molecules. So the Lewis diagram. So now I need you to go back and think about those basics when drawing Lewis diagrams. I'm going to have an F, and it's going to be singly bonded to another F. And then how many lone pairs of electrons is on that fluorine after it bonds like that? How many? What do we got? 3 pairs, because fluorine has 7 electrons in its outer shell. It shares the 1, so I need to draw these extra electrons in. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right? Now, in terms of the energy level diagrams, I've actually got some of these pictures that I can just pull and bring in nice circles and rectangles. But I think it's important for you to see when I see the way I build this. So in terms of the energy level diagrams, I'm going to need 2 fluorine atoms. And I'm going to put them above and below of each other. Fluorine goes back to helium. We're always going to use the core, helium. I then am going to have a 2s and then 2p. And I'm going to draw the second one there. I'll put the electrons in a moment. Helium, 2s, 2p. And let's put our 7 valence electrons in there. And if you start to think about how the Lewis diagram is going to represent in the energy level diagram, each of those fluorines has 7 electrons in them. One of them's got to pair up with another electron in the other fluorine. So it's looking like this. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And I'm not worried about the spin being correct this time. And I'm hoping that you can see there's a single electron in the last p orbital here. There's a single electron in the last p orbital here. We can connect them together. I just use a rectangle to connect them together. And when we have a P overlap with a P, again, that's a sigma bond. All right? Now, I'm going to draw the orbital view on the board, which I'm not bad at it. And then I'm going to use my little shortcuts that I made to make it look a little better, so that when you see me bring up the shortcuts, you can see how this is made. So the orbital view, I'm not going to worry about the 2s orbitals right now, but I'm going to worry about the p orbitals. There are 3 p orbitals, one that goes up and down, one that goes left and right, and then one that goes in behind and comes out front. I want you to try to draw that. And on my little simulation, they're going to be fatter, because really the p orbitals are a lot fatter. If I were to draw the p orbitals in the actual way in which they look, my picture would look more like this. One lobe would go up like this, and the other one would go down, almost like more like an 8 than a dumbbell. The second one would go out like this, and then out like this. And that becomes really complicated to think about and look at. The third one sticks out this way and back that way. So it's really kind of a pain to actually draw it the way the p orbitals exist. So we draw them as longer, skinny orbitals. Okay? Now, in this particular picture, I'm going to have my 2 electrons. This one is full. That's represented by that first box. The front and back one is full. Notice I've put the 2 electrons in one of the lobes, but they don't have to be. They can be existing anywhere in the front or the back or the top and the bottom. They're just going to be there 95% of the time. Now this one is where I'm going to have the overlap, and I'm not going to draw it in yet, but there's only one here, which means I need to draw another fluorine so that it overlaps end to end on that p orbital. So it's going to look like this. I'm really going to draw the same picture, except it's going to start over here. I'm going to get a different color here. Yeah, we'll go with that one. And there's the 1p orbital right there. That's the px. And that's the one that's going to overlap. It's also going to have a py. There it is there. It's also going to have the z coming out front and then kind of hiding in behind. Notice I use some dashed lines to represent that it's hiding in behind, so that it's like getting further away from us. And again, in this particular thing, full, full, and now we've got that p orbital, and right in here, it's actually going to add to make a nice big bump in the middle, just like the 2 H's that I drew. It's going to make a nice big orbital in there in the middle, but I'm going to just represent it like this, and it's got the 2 electrons in it right here. 1, 2. I wish I had it a little bit bigger, because I'd like to make in that space a little sigma as well. I'll put it down below, a little sigma. Again, if I were to draw it in actual size, they would be much larger. Now, with the computer, I get to cheat, because what I did is, in order to make this kind of look a little nicer, I drew some pre-made orbitals. So if I want to grab an XYZ, I can just grab an XYZ. I can put it right there. Nice and easy. A little cheating, but it makes it quick. So I could grab a second XYZ, and I can have it overlap right there. Put it right there on the spot. And I essentially have the picture that I just drew, except I did it a lot quicker. Again, in the middle here, we would have our shared pair right there, and right there is our sigma bond in there. So I'm going to be pulling these out, and I'm hoping you can draw it like this. That's why I wanted to show you the first way I drew it. Now, in reality, there's also a couple of s electrons in here as well, but I'm not going to draw those in all the time. We have the 2s electrons. They're in there. They're in their little sphere. Okay? So that's the way an F2 molecule looks. It has all of these different orbitals, and they're overlapping, and we've got that sigma bond in between. Okay? 3D Lewis, in this case, doesn't have any meaning because it's just linear. I guess this is three-dimensional, but when we look at a bond, when we look at atoms, we can't actually see the orbitals. When chemists look at molecules, they can look at them using things called X-ray diffraction. They can use something called neutron diffraction. They can shine X-rays at a crystal of F2, and then what they see coming out the back, they can do calculations and work their way back to locating the actual nuclei. And when you look at molecules in these fashions, you can only locate the nuclei. So what does this thing look like to an X-ray diffraction? You see a nuclei there and a nuclei there, so we assume that there's a bond in between. It's a line. It's linear. So it's not really a three-dimensional molecule. We don't have to worry about a 3D Lewis representation of that. We will eventually when we get to more complex molecules. All right? Let's look at another one. HCl. So now I'm hoping I've armed you with enough information that you can start drawing things without me. HCl, I think we could easily draw a Lewis diagram. You can come up with the energy level diagram for H and the energy level diagram for Cl. And I'm obviously leaving lots of space here. For Cl, we're going back to neon. Doesn't matter what order you do it in, whether you do the Cl first or whether you do the H first. I like to do the simple ones last, and you'll see why. So we're going back to neon. And it's going to be, I think, a 3s and 3p. And fill it up as you know how. 1, 2, 1, 2, 3, 4, 5. So we've got a p orbital that's half filled. It's going to need a partner. Now that I see where I've positioned my last p orbital, I could have had the first one be the one that's only half filled. It doesn't really matter. I can now position my H down underneath it, because I'm kind of looking ahead. You could put it above as well if you'd like. Good move there. Doesn't matter where you put the H. 1s, got an electron in it. I don't think it's too crazy to put a box around that and call it a bond. And it's also a sigma bond. So here's where now, due to the technology, I get to cheat a little bit on the orbital view, because what I can do is I can take my 3 p orbitals that represent the chlorine, and off on the end of one of them, and I always like to put it on the X one just because it's convenient. We can think of it horizontally. It also will look like our Lewis diagram. I'll take one of my orbitals, which is a nice little 1s orbital, and I'll just put it over there on the side and have it overlap. And again, just to finish it off, this guy is full, right? That's the up and down one. The one in front and behind is full. And I don't give really enough overlap, but I'll put it in there, up and down right there. That's where that overlap is. And that also is a sigma bond. Okay? All right. I think it's kind of neat. I like the orbital views. They look like flowers. Really. Beautiful. All right. Now my next example, did everybody get that? So my next example, now, and here's just a graphic I found online with some various types of sigma bonds. So there's the H2 with the 2s orbitals overlapping. There we've got F2. So there you can see the p orbitals overlapping. It becomes larger in the middle, a greater probability of finding the electron in between. And then here we've got HF, and I didn't represent it as that kind of aggregate, but that's the way it would look. All right? Now let's talk a little bit about carbon. Hold on one second. Do I want you to draw that? Let me just jump ahead. I'm going to just give it to you straight up. I'm not even going to, I've sometimes asked this. I'm going to let you write the whole thing, and you can write that whole slide. Just write the whole slide. We all know that carbon has the ability to form 4 bonds with adjacent atoms. We already know from last year as well, those bonds can be single, double, and triple bonds. Right now we're just dealing with the single bonds, which are sigma bonds. It's also very well known that the shape of a carbon atom that contains 4 single bonds or sigma bonds is what we call a tetrahedron. That has been observed through, again, these processes that I quickly mentioned, things like X-ray diffraction and neutron diffraction. That has been determined very well to be a perfect tetrahedron, especially for CH4, because they're all the same, the H is on the end. If we look at the angles in the atomic orbitals for carbon, we'll see that there are 2 unpaired electrons, and they should be 90 degrees to each other, because our p orbitals are all 90 degrees to each other. So if those lone electrons were to form bonds, the angles between the bonds should be 90 degrees, and they're not. When chemists look at the angles, they see this tetrahedron structure, and the angles are all exactly 109.5 degrees. So an idea or a theory was needed in order to explain what's taking place in terms of these shapes. This theory or this idea is called hybridization theory. Again, keep in mind, all of these orbitals are actually wave functions. They're mathematical equations that describe where you're going to find the electrons in terms of 95% probability, and they're all waves. Waves can be added together. Waves can actually also be subtracted off. You can take, in music, if you have a synthesizer, you can generate all kinds of different sounds by adding various waves together. You can then tell the computer to subtract waves off and still change the sound. So you can add waves together mathematically. You can then dissect waves into individual waves. So what hybridization theory does, it mathematically takes the 4 orbitals, the 2s and the 3,2p, and it mathematically puts them together into one big wave function. It's just adding waves together. And then, because chemists know that they must be identical orbitals pointing opposite directions, they simply took that wave function and divided it into 4 identical wave functions. And that mathematical addition of the wave functions and then dividing it into 4, we say they've created hybrid orbitals. Hybrid orbitals that are formed by putting together the wave functions we see according to quantum theory. So, in this particular hybridization, we're taking an s orbital and we're adding it to 3 p orbitals. We always need to get out the same number of orbitals, so we start with 4 orbitals and we're going to end with 4 orbitals. But now they're going to be called sp3 orbitals because they've been made by an s and 3 p's. And their energy is going to be all exactly the same. We've done a slight little promotion for one of these electrons. And their energy will actually exist somewhere in between the energy value for the s orbitals and the p orbitals. It'll actually be a little closer to the energy of a p orbital because we've added 3 p-type orbitals and just 1 s-type orbital. So if you do the mathematics and average it out, the weighted average gives you energy that's a little closer to the p orbitals. And with distributing the electrons, now because we're using our Aufbau principle and all of the orbitals are the same energy, we have 4 of them in each of the orbitals. All right? Now this is a little bit of a promotion, kind of like our special case, because this electron down here, these 2 in the s, had to gain a little bit of energy in order to make this change. The energy for that comes from the formation of the chemical itself. As the H's are approaching the carbons due to being attracted electrostatically, they're bringing kinetic energy with it. That bringing together of the H's will automatically result in this hybridization, and it takes a little bit of that kinetic energy that it's bringing in as it's reacting. It hybridizes, and they stick to the side, and we get this particular view. All right. Now I'm looking at this, and I'm going to stop right there. Now hold on one second. I do want to give you a few more. I was hoping to get to the end of hybridization. So at this point, you need hybridization for the last 4. I guess do 2 more examples at home for practice, HF and Cl2. You can do those without hybridization. No need to hybridize those particular ones. This is just to kind of force you to go home and re-look at it again and, think it through. It would have been nice if I could have got to the hybridization examples, but I don't want to rush it at this point. We'll look at hybridization again tomorrow. We'll keep on going from there. All right?